Okay, I think we can start now. I have 50 participants and can't waste more time. We've just waited for 5 minutes. All right. So, last lecture, we were discussing about loop unrolling and scheduling. Anyone who will tell me why we were doing it?
So that the need of stalls can be uh,
Eliminated,
मतलब
yeah.
हटा सकते हैं, yes.
Bilkul. So we want to eliminate stalls into the pipeline. So any code that is pipelined might require certain stalls to overcome the hazards. And scheduling is one of the best ways to overcome the hazard. The reshuffling of instructions, of insertion of independent instructions between two dependent ones, allows the instruction also to get executed and no stall to be introduced. So it is the best way which is used to overcome hazards in the pipeline. But then, every time finding an independent instruction might not be possible. So what the compiler of this TLX processor does is it opens the loop. So if we have a loop kind of if I have an program which has a operation which is carried out in a loop, right? And that loop, if we observe that all the iterations are independent of each other, as in we talked about last time, we had an array of 1,000 values where every time each value of the array was added to a constant and stored back to the same memory location. So if we just observe this constant and the values, every all the iterations of this loop, 1,000 iterations, were independent of each other. So every time the data would be picked up, added to a constant, stored back to the same memory location, and again for the next one it would carry on in the same manner. Now, since all these operations were independent with respect to each other, the compiler could open the loop as number of times as it feels convenient, right? So loop unrolling is performed by the compiler. We did this program with the respective stalls. If you all can recall, without scheduling, the average CPI turned out to be 2 with stalls introduced into this code. This is what we discussed last time. Yes, so with stalls introduced into the code to overcome the hazard, we had the average CPI excuse me, as 10 by 5, that turned out to be 2. And then we scheduled the code to see how much was the average CPI. In this case, it turned out to be, I guess, 1.5. So it was 1, 2, 3, 4, 5, 6. So 6 clock cycles by 5 inches, 1.2. This turned out to be 1.2, but we still would want it to be more efficient. We would want the average CPI to turn out to 1 so that we can exploit the maximum parallelism from the available hardware. Now, this is what the compiler did. The compiler unrolls the given loop as number of times as it feels as an optimized value, right? Currently, are you all getting?
Yes, ma'am.
Right. So currently the loop is opened 4 times. Load from the respective memory location, add to a constant, store back to the same memory location. Since it is in descending order, so your base register, see, the compiler cannot touch the thing which is the value which is there in the registers, but it can definitely play with the displacements, right? So if you all remember, branch not equal to 0 r1 comma target, that target value which was in terms of displacement was also was also calculated by the compiler only. So the compiler is efficient enough to calculate this displacement and play with the displacement also. So earlier the displacement was 0 r1, now it becomes -8, right? And since next 8 locations have to be picked up, so again added with the constant and data stored back to the same memory location. Then third load, so again next 8 locations, so becomes -16 r1 and added to a constant. I hope you don't want me to elaborate more. I spent last entire lecture on this.
Yes, ma'am.
ये ठीक है ना? फास्ट तो नहीं
Yes,
जा रहा?
ma'am.
Yes, ma'am.
अच्छा ठीक है. So then the loop opened for the third time. Again data picked up from -16 r1, 8 bytes of data into f10 and f11, added to constant in f2 and f3, and the result stored back to the same memory locations again. So 8 locations again referred to. And the last loop iteration would be to load from -24 r1 at constant, store back to the same memory location. Now see, since uh, we have fetched 8 bytes 4 times. Where is my marker? Yeah. Just a minute, let me get the marker, no, it becomes easy to explain. Yeah, so if we just see, um, loop opened first time, loop opened second time, loop opened third time here, and fourth time here, right? And every time we are fetching 8 bytes in one go. So this means 32 bytes have been already fetched. Obviously, the base register should be decremented by 32 now. So R1 becomes R1 minus 32, and since it is not equal to 0, it will jump back to the loop wherein R1 is minus 32, and now you are talking about 0 R1. This means minus 32 R1 is the next location that you are referring to. And the next loop again says minus 32 plus minus 8 makes minus 40 R1 as the next 8 locations. Then minus 48 R1, and finally minus 56 R1, right? Are you all getting?
Yes, ma'am.
And it
Yes,
keeps
ma'am.
on moving until the value of R1 becomes 0. The moment it becomes 0, then the loop exits and it can come to a halt, right? So just opening the loop 4 times and making it execute 250 times will give me the same results as I was executing single loop 1000 times, and will take the same amount of time also. Am I right in saying that? Will it take the same amount of time if I open the loop 4 times?
No, ma'am.
Okay, so why no? Justify.
Because मैम जो पिछला वाला था उसमें there were stalls in between, but
Forget
herein
about
there
the
are.
stalls. Forget about the stalls. If I just talk about an ideal situation, say maybe that this loop is running without any stall earlier, right? And I execute this loop 1000 times, and now I open this loop 4 times and make it execute 250 times. So we're talking about an ideal situation. Will the time taken be the same?
Yes, ma'am. The
Yes.
points are.
Yes, it will be the same. Definitely, it will be the same. And that is why this is the main foundation block why loop unrolling and scheduling is actually possible. See, earlier also one loop was executed for 1000 iterations. Now, four loops are executed for 250 iterations. It gives the same value, same results, takes the same amount of time ideally, right? But the point here comes is that if we just talk about the previous code, we discussed that after scheduling also we could result in a CPI, average CPI of 1.2. Our main aim is an average CPI of 1. So this is why actually the compiler opened the loop. So you know what it does, it because if it has opened the loop, it has created multiple options for itself. Now reshuffling is much more easier to perform. It has lots and lots of instructions wherein reshuffling is possible. Earlier it just had 4 5 instructions. So there was a limited scope. Now, even though the same code, I mean, ideally is taking same amount of time as the earlier one, but the processor or processor's compiler has how many instructions? 14, if I'm not wrong. 1, 2, 3, 3, 4 is 12, and then 13 and 14. So 14 instruction it has, and it has an ample opportunity to reschedule this code. And this is what it does. But before rescheduling, let us see what is the CPI that comes. Yeah. Oh, this is the okay. I'll just calculate from here, and maybe I did not bring it in the last lecture also. So if we just see, there was a requirement of one stall here. If you all can recall, two stalls here. Remember,
Yes, ma'am.
है ना? अब यहाँ तक एक iteration हमारी complete हो गई. So loop unrolled once makes 1, 2, 3, 4, 5, and 6. 6 clock cycles for one unrolled loop. That's clear?
Yes, ma'am.
So I'll just write this. So 6 clock cycles, right? Now this loop is executed 4 times. So 1, 2, 3, and 4 till here. Till here, if I see, it is executed 4 times, right?
Yes, ma'am.
Makes 24. 6 4 is 24. So 24 clock cycles till here, right? Now between subtract and branch, I don't think we require a stall because forwarding can do the job. And then one stall here. So 3 more makes 24 plus 3. समझ आ रहा है?
Yes, ma'am.
Is equal to 27. What about others? Pratyush Anand, is it clear? Speak up. Is it clear? I need an acknowledgement from someone else. No, Nirmati is not the only one who's in the class.
Ma'am, it's clear.
All right. So there's a message on chat. Yes, ma'am. Okay, fine. Yes. So this makes 27 clock cycles, and by 14 instructions, again an average CPI of 2. Right now. So what the processor does is it now reschedules the code, and rescheduling it does in such a manner that if it performs all the loads together, all the adds together, and then all the stores together. Let's see what happens, right? So I'll just move this on. Yeah. Excuse me. Yeah. If we just see here, load for the first 8 bytes into F0 and F1, load for the next 8 bytes in descending order into F6 and F7. So the same code, it is only shuffled now. Load for the next 8 bytes from minus 16 R1 into F10 and 11, and load from the next 8 bytes from minus 24 R1 into F14 and 15, right? Do we require any stall here in between?
No.
They're all
No.
independent,
No.
no problem. Very good. So no problem, no stall required here, done. Next, we add F2, F3 to F0, F1 and store in F4, F5. F0 and add were earlier separated by one stall, remember?
Yes, ma'am.
There's no need for this stall anymore. I have inserted 3 instructions in between. Next, add F8, add F6, F7 to F2, F3 and store in F8, F9. I think there is no problem here also. So this instruction and this instruction were earlier separated by one stall. Now they are so far apart, they're not going to cause any problem to each other while in parallel execution. Clear?
Yes, ma'am.
Okay. Similarly, F1011 added to F23 and stored in F1213, and F1415 added to 23 and stored in F1617. So till here we observe that we have actually removed the entire need of stalls between 8 instructions. यहाँ तक कोई प्रॉब्लम नहीं. ठीक है. Now let us start storing and see if there's any problem. So if we just start storing, the first result is available in F4, F5. So we store it in 0 R1 back, and earlier this add and this store were separated by 2 stalls. Now there are 3 independent instructions in between. Again the problem of stall is resolved. Next one, from F8, F9 we are storing to minus 8 R1. Again these 2 instructions were also separated by 2 stalls. Now we have 1, 2, 3 instructions in between. The stalls are all gone. There is no need. वही 3 clock cycles जो उसको stall से wait करना था, उन 3 clock cycles में अब 3 instructions execute हो जाएंगी, तो तब तक उसका result produce हो जाएगा, ये hazard भी clear हो जाएगा. ठीक है. अच्छा,
Yes, ma'am.
अब अगर इसके बाद after this, if we would have performed the store double. Okay, let me just hide this. I can do it like this. Yeah. So if we now perform, say, the store double of F1213 to minus 16 R1. Suppose this is written 16 R1, but just to illustrate, if we did not have this reshuffling done, what was the result? That's what we want to illustrate right now. Okay. So if we just see, if F1213 was stored to minus 16 R1 here, if F1213 was stored to minus 16 R1, it should not cause any problem here also. It will not lead to any hazard here as well. It is again separated by 3 instructions, no problem at all. But for the future instructions, if we see the branch, the branch instruction has one stall, which is the branch delay slot. And in any case, we want the branch delay slot to be occupied with one independent instruction, right?
Yes, ma'am.
So the last store, see, either we could have rescheduled the code such that this subtraction of R1 is done at the end. It will always get executed because it is in the branch delay slot. This was one option. Or right now, what the compiler has already done, it has subtracted R1 by 32 earlier. So R1 becomes minus 32 R1, right? Next, if I have to store the value of F1213 at minus 16 R1, this means I have to change the value of displacement to plus 16. Getting?
Yes, ma'am.
Everyone?
Yes, ma'am.
Okay, good. This is just one option. The other option again I'll discuss again. Then it checks if R1 is not equal to 0, go to loop, and in the branch delay slot we have inserted one store as from F16 to Y plus 8 R1 now.
Because now the location is minus 16 के बाद हमें minus
Minus
उस पे
24.
जाना है.
Yes, very good. So we want minus 24 R1, right? This was minus 16 R1 earlier. This was minus 24 R1. So 32 minus 32 plus 8 gives me minus 24 R1. The compiler of a RISC-based machine is efficient enough to convert, to play with the displacement values, right? So it can always change. So it's written here also, 8 minus 32 gives minus 24. This is just one way of rescheduling. I could have done something like this also. So the processor can do something like this. It sees actually what is the most optimized one. So it can just introduce this instruction here, right? And then rest all stores could be brought together. There was no stall requirement between subtract immediate and branch not equal to 0. This was overcome by forwarding, if you all can recall. This produces the result in the execute stage, and this uses the result at the end of the execute stage. So there was no problem. Getting?
Yes,
Yes.
ma'am.
So we could have done this way also. This is one way which is illustrated in the book. Even if you write a rescheduled code which is absolutely correct according to the logic, you will get marks, right? So we could have moved the subtract immediate here and then not play with the displacements anymore and let the program run on its own the way it was running earlier. So all stores together and then subtract immediate, देन ब्रांच नॉट इक्वल टू जीरो. फिर उसमें एक प्रॉब्लम आती थी कि आपका ब्रांच डिले स्लॉट की प्रॉब्लम आ रही थी. इफ यू वुड हैव डन इट लाइक दैट तो आपका ब्रांच डिले स्लॉट की प्रॉब्लम आ जानी थी ना कि उसमें आप क्या डालते. गेटिंग?
Yes, ma'am.
Because
Yes, ma'am.
you have to check R1 after it is updated, so you have to subtract R1 earlier only. So any type of reshuffling which leads to right results will suffice the purpose. There is no problem. This was just one alternate that we discussed. Okay, so let's see what is the average CPI in this case now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 by 14 makes an average CPI of 1 without any need of stalls. So this was the main aim of loop unrolling and scheduling. And I'll just start with a new topic. Anybody has any doubts in this loop unrolling? You can ask me right now.
Ma'am, how will we get to know कि हमें कितनी बार unroll करना होगा loop?
सी ये तो कंपाइलर डिसाइड करता है. ये तो कंपाइलर हमेशा खुद से डिसाइड करता है. इट रन्स एन एल्गोरिदम टू चेक व्हाट इज द ऑप्टिमाइज्ड वैल्यू ऑफ अनरोलिंग रिक्वायर्ड. बट अगर आपको एग्जाम में आता है तो इट विल बी मेंशन अनरोल द रूप टू टाइम्स और मे बी 3
Okay.
टाइम्स. So that will be mentioned.
Okay.
Any other doubts? Nothing? Okay. I have uploaded the remaining chapter 3 video lectures on the LMS platform yesterday, and on the classroom also I'll upload in the coming days. So do go through them. And one announcement that I made in the tutorial also, you might have an EST which is in face-to-face mode. So we might call students in batches, year-wise, and based upon social distancing norms, we might conduct the papers. Excuse me. So be prepared and study the subjects accordingly, not just my subject, for all the subjects. Take it seriously, because at the end of the day, nobody will remember that 2020 was a pandemic. Everybody is going to, just look for the quality. And if you all want to get placed in future, well placed, you need to get thorough with the subjects. These are all required in industry. All right. Yes, let's start with the next chapter. This is memory hierarchy to improve the processor performance. So, what is memory hierarchy, anyone? What is memory hierarchy? कौन बोलेगा? Drishti Goyal. Her mic is not showing up. Let me ask someone new. Tanish. Tanish, unmute. What is memory hierarchy according to you? If you're there in my class, either send me a chat message if you don't want to speak up.
Yes, ma'am.
So, what is memory hierarchy, Viche?
हम जो डिफरेंट लेवल्स होती है मेमोरी की, जैसे प्राइमरी सेकेंडरी मेमोरी, फिर रजिस्टर्स, कैश मेमोरी,
वेरी गुड.
वो
और
स्पीड वाइज डिपेंड करती है सारी.
वेरी गुड. और क्यों जरूरत पड़ती है मेमोरी हायरार्की की?
हम हर जो भी टास्क अपन परफॉर्म करते हैं उसके लिए अलग अलग स्पीड्स होती है ना. जैसे अगर अपन को कोई प्रोग्राम लोड करना है तो उसकी स्पीड फास्ट होनी चाहिए, पर जैसे अगर डाटा को स्टोर करके रखना है तो उस चीज के लिए अपन को एकदम हाई परफॉर्मेंस मेमोरी की जरूरत नहीं रहेगी ना, कि जो
हाँ.
बहुत फास्ट रहे.
Very good. So optimization of performance,
Yes, ma'am.
optimization of speed, and because there are certain applications which do not require a very high speed. There are certain applications which have to be done at a very high speed, and accordingly, if we procure a memory and attach it to a processor which is either very fast or very slow, we actually limit the processor's maximum capacity of gaining speed, right? So we follow memory hierarchy, and we have different levels of memory. So I'll just come to it. So we follow different levels of memory hierarchy so as to optimize the processor's performance in terms of speed and output, right? So with the CPU, we have the immediate memory which is available is registers. Then, if we start following in hierarchical order and size wise also, we have cache followed by main memory followed by your virtual memory. And if we talk about semiconductor wise, cache is made up of CMOS SRAM, static RAM. Your main memory is CMOS dynamic RAM, and your virtual memory can be hard disk, it can be a magnetic disk, it can be an optical disk, it can be a flash drive, right? Let's just talk about their speeds. So this is a very the data that I've picked up is quite an old one. Currently, if you talk about the memory reference, how much is the size of RAM available in market right now?
Ma'am, 32 GB to 64 GB, around the same.
इससे भी ज़्यादा है, इससे भी ज़्यादा है, इससे ज़्यादा भी है आई गेस.
मैम टीवीज में चली जाती है.
टीवी में आ रही है.
नहीं, मेन मेमोरी की बात कर रही हूँ मैं.
जी मैम, टीवीज में आने लग गया आजकल.
आने लगी है. Okay, so that is really again a news to me. I heard about GB only. So I was about to say that it is reached up to a GB value, but it is reached terabytes also. So when we just talk about the memory hierarchy in terms of size comparison, right now what I found from the literature, your registers usually are in bytes, cache in kilobytes, memory, that's what I was saying, the main memory has now reached GB and maybe terabytes also right now, and your hard drive even higher than that, right? So when we talk about these memories respectively, their access speed varies. So when we talk about registers, they are the fastest. So that is why we always prefer to have more registers in any processor. This makes the computation more faster and easier. So of the order of nanoseconds, ये तो bytes के हिसाब से है. Obviously, If the order of memory increases, the speed improves accordingly, right? So 5 nanoseconds for your registers is the access time. For cache, it is 10 nanoseconds on an average, I am saying. For main memory, around 100 nanoseconds, and for your secondary memory, around 5 milliseconds, so of the order of milliseconds. So now, accordingly, if we talk about speed, cache is the fastest, smallest. Main memory, a little slower, but still faster than the hard drive or the secondary memory. And definitely, we need these levels of memory to optimize the processor's performance. We would always use secondary memory for what? ये क्यों यूज करते हैं?
Storage.
हाँ, main storage of all the, it acts as a junkyard to store all the programs and data. Everything is here, right? A subset of it is created here, and then the program runs here much faster. Then obviously it takes more time on the secondary memory. Then definitely we want to improve the speed even more, so we move on from main memory to a smaller chunk of memory called cache. So I guess we discussed this earlier also, and you must have discussed this in your other subjects as well. This is a real hot topic these days and mostly asked in placements. So we must be thorough with these basics. And then when I say your main memory is a subset of your secondary memory, what about cache?
Cache is a subset of the main memory.
Right. It is actually, see, whenever we talk about a subset, it does not mean that it is an exclusive subset. It is an inclusive subset. This means whatever is here, a copy of it is created here. It still remains here, right? So the major, you can say the backdrop storage is still available in the secondary memory. A copy of it is created in the main memory, and then a copy of it is created in the cache. And there is a logic which is used for creating these copies. What is that logic? What is that logic? ऐसे ही कुछ भी उठा के कहीं भी डाल देते हैं. कुछ तो फॉर्मूला यूज करते होंगे, कुछ तो एल्गो यूज करते होंगे, कोई लॉजिक तो फॉलो करते होंगे.
जो frequently used होती हैं
Right.
programs या
Very good. So we discussed about Amdahl's law, and the same application comes here as well. It is based upon principle of locality, which says that most commonly used instructions and data in a program are brought and kept in smaller memory buffers, which are much faster than maybe the secondary memory or the main memory, right? So therefore, memory hierarchy came into being with cache as the first. See, we don't count registers actually, because they are inbuilt with the CPU. So we don't count registers in hierarchy. We start counting from cache. We can have different levels of cache. Level 1, level 2 cache. We can have data cache. We can have instruction cache. So cache with different levels, and then followed by your main memory, followed by the secondary memory. Till here is clear, everyone?
yes.
Okay. Now, let's start with cache. So, cache is the smallest, fastest, and nearest to the processor. It is basically using the SRAM semiconductor technology. It is volatile. When I switch off the power, cache gets empty. So, for the first time, when I switch on the power and I access a program or a data from the memory, the address that goes to the cache always sees the cache empty, right? And this is called as we call this scenario as a cache miss. So cache miss happens, and cache miss causes wait states or stalls to be introduced. अब इसका रेफरेंस मैंने आपको डेटा हजार्ड्स में दिया था, मुझे कोई बताएगा मैंने कब दिया था इसका रेफरेंस?
Ma'am, memory stages take place needs two clock cycles.
Very
उसके
good. So in the WAW and the WAR hazards, if I remember, I gave you this reference. So there's a chat message says, "Ma'am, please repeat cache miss." Okay. See, when we talk about this memory hierarchy, let me come to the other slide. It becomes easier to explain. Yeah. If you just see the memory hierarchy, after the the registers are inbuilt with the CPU, so these are not counted in the hierarchy because these are inbuilt, right? The hierarchy starts with cache. It is cache followed by main memory followed by secondary memory or virtual memory. Now, all programs and data are stored here. Is RAM volatile? Anyone? Is RAM volatile?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
yes, ma'am.
So is your cache also. So RAM and cache. When we say RAM, it is actually your main memory, right? So your main memory and cache both are volatile in nature. If I just specifically talk about RAM and your cache, right? Now, from the processor, if an address goes on the address bus, obviously it has to look for a given address and it starts, searching in the hierarchical order. तो सबसे पहले connections में आई आपकी cache. Since cache is volatile, after you have switched off the power and switched it on, you find all the locations empty. The processor finds all the locations empty, and when they are empty, it is a cache miss, right? ठीक है? Now,
Yes, ma'am.
it goes to the main memory. So, in the main memory, it specifically talks about the RAM right now. ठीक है? RAM is also volatile, so it does not find anything here as well. There is a main memory miss. Right? Now, it has wasted some time to search for a for a memory location in cache, and then some time to to look for a memory location in main memory, right? And these clock cycles which it has wasted are nothing but stalls. ठीक है?
Yes, ma'am.
Hmm. So so these stalls, I was saying that we had this reference in your data hazards as well. So I was writing this code just to tell you that we discussed about the WAW and the WAR hazards, wherein the second instruction proceeds and the first instruction is still hung up because it has a memory reference. So maybe the next instruction is add R3. समझ आ रहा है? Are you all getting?
Yes, ma'am. Yes, ma'am.
R3 comma R2 R5 R5 comma R1. Now see, if you just see these two instructions, load word into R1 from 0 R2, which is a memory location, and then it says add R3 R5 and R1. So R1 has to take the data from the memory, which is from the previous instruction, which is loaded from memory, right? Now if this everything proceeds in the right order, there will not be any problem. But if the current instruction, the load word instruction, goes to the cache and there is a memory miss, and then it goes to the main memory and there's again a memory miss, it has wasted certain clock cycles and stalls are introduced. So this instruction is still hung up while this one proceeds in the pipeline, right? And if such a scenario happens, this leads toward WAR hazard. And this will proceed if there is some bypassing followed in between. Otherwise, इसके पीछे वाली अगर वो stall करेगी तो ये भी stall करती है, right? By any means, if first one stalls and the next one moves on, it leads to a WAW or WAR hazard. This reference I gave you earlier also. This is what I was saying right now. Okay. So not to confuse you anymore, let us just come back and see that if the address goes from the CPU to the cache for the first time, it is empty. After power is switched on, it incurs a cache miss, right? Then it goes to the main memory. And from the main memory also it incurs a miss, and then it goes to the secondary memory. Definitely it is going to take much more time, but from the secondary memory, the respective, see, it is the main storage house. So the respective instruction or data is picked up, put on the data bus, brought to the processor. Side by side, a copy of it is created in the main memory and a copy of it is created in the cache. Getting?
Yes, ma'am.
And this is how your main memory and cache fetch their data, right? And then these have smaller capacity, even the main memory and cache both have smaller capacity than the secondary storage. And definitely there has to be certain policy of placement and replacement of data followed in cache as well as in main memory. And then if something is being transferred from here to here, there has to be a log register which has to be maintained, how how your address translation is taking place. Are you all getting?
Yes, ma'am.
Yeah, I'm just telling the basics right now. We will move on to explicit details after, um, maybe this lecture, after this lecture. So the logbook that maintains all the address translations is called as a translation look aside buffer. So if data is being transferred from a higher memory, larger memory to a smaller memory, obviously, if you have 3 bits of, if you have 3 locations and each with 3 flip-flops, right? How much maximum data can you store? I'll repeat my question. You have 3 locations as 3 flip-flops. How much maximum data can you store in these 3 locations? Bolo bhai.
3 bits.
3 bits. It is 3 bits and the combination is all 3 zeros to 3 1s. Maximum 8 datas, right? So it can be 0 0 0 to 1 1 1. बीच में टोटल यहाँ से मिला के यहाँ तक आपके पास 8 कॉम्बिनेशन आ जाएंगे, ठीक है? अब ये सपोज 2 बिट्स का स्टोरेज है और ये एक ही बिट का स्टोरेज है. जस्ट गिविंग यू एन इलस्ट्रेशन, राइट? नाउ if you are transferring from 3 bits to 2 bits, obviously you require a lesser address size as well. Getting?
Yes,
Yes.
ma'am.
And if you're moving from 2 bits to 1 bit, you definitely require even lesser size than that as used here. Getting?
Yes, ma'am.
All right. So I presume कि अब तक जितना बताया सब समझ आ गया है, and I'll move on now. यहाँ तक clear है? कोई doubt है तो बोल दो. Anybody has any doubt can ask right now. No doubts. या तो सब समझ आ गया या कुछ भी समझ नहीं आया. Nothing? I can repeat if you want. See, it's a very important topic. We have memory hierarchy and we follow memory hierarchy to optimize any processor's performance in terms of speed, right? Obviously, a larger chunk of memory will store a larger amount of data, but at any time, all the data and all the instructions are not required. So, if we have to operate on these data and instructions in a faster way, we use faster, smaller memories, which is the main memory and the cache. Cache being the fastest, followed by main memory in terms of speed, followed by virtual memory, right? Cache is volatile, so is your RAM. So when power is switched off and switched on in the first go, cache and main memory both will be empty. Obviously, it's a volatile memory, everything will get erased off, right? And then when your address goes from the CPU to the first level, it incurs a cache miss. Some stalls are there, some time is wasted. Then it goes to the main memory, there's a main memory miss. and then it goes to the virtual memory from where it fetches the required data and instruction. Definitely takes some time, and then it creates a copy. It creates a copy of the respective data and instruction in the main memory and a copy of it in the cache. Cache being smaller in size will require a lesser addressing in terms of bits, I'm saying, address size, than the main memory, and main memory will require a lesser address size than the virtual memory, right? Now, if something is moving from here to here to here, the processor maintains a log register wherein it keeps a track of what has been transferred where. And this logbook is so efficient that for every transfer it is updated. I hope till here is clear, everyone.
Yes, ma'am.
Good. And this logbook is called as a translation leukocyte buffer. We will study each and everything in detail in the coming lectures, but now let us start with the step-by-step process. So we discussed that cache memory is smallest, fastest, and nearest to the processor. It can store programs. See, the programs are stored based upon principle of locality. We must not forget this, that all the filling of cache and main memory is taking place on the basis of locality. And locality says most recently accessed, most frequently accessed data and instructions have to be stored into the cache, followed by main memory. Right. Moving on. जहाँ पे डाउट होगी ना बच्चे मुझे पूछ लेना. You can always send me a chat message also. There's no problem. Now your primary memory is also known as the main memory. It is fast memory used to store programs, and then this memory consists of 1-bit storage cells and can be read or written individually. The data is stored in fixed size cells called words, and the word length, ये हमने शुरू में पढ़ा था. The word length of any computer may be defined as 16, 32 or 64 bits. ये क्या होता है word length? Anyone who would like to speak up?
Ma'am, word length is the amount of bits a processor can मतलब एक जगह से दूसरी जगह एक बार में कितनी उठा सकता है एक बार
वेरी
में.
गुड. तो एक बार में वो कितना ट्रांसफर कर सकता है, ऑपरेट कर सकता है और रिजल्ट प्रोड्यूस कर सकता है. करंटली हम जिस प्रोसेसर की बात कर रहे हैं वो उसकी वर्ड लेंथ क्या है DLX की?
32 bits.
32.
Absolutely right. It is 32 bits. When we talk about the MIPS processor, we have 64 bits and 128 bits version also available now. Okay. Now moving on. Each memory location definitely must have its own address. This is for the primary or the main memory. Now coming to secondary storage, in addition with primary memory, we have a less expensive permanent secondary storage for storage of large data and programs. This is definitely slower than the primary memory, and some basic examples are, can you tell me a secondary memory in your day-to-day usage?
Flash drive.
Yeah, the flash drive that we use. Then your hard disk that we connect externally. We have internal as well. We have the optical discs, which are CDs and DVDs. So all are. Have you all seen a floppy drive? Have you seen a floppy?
Yes, ma'am.
Yeah. So floppy was also a form of secondary storage, though it's become obsolete now. But I guess we all should know about it. How much is the time left? I just have 2 minutes left. I have to explain you about how cache is filled and how the data is replaced. So the read write operation in cache, I have to explain you about that. Any doubts still here? I can clear, and then next lecture we can start up with the basic operation. No doubts?
No, ma'am.
Okay, we will be announcing the quiz date soon, because yesterday we had a meeting with Doa, and there he said that at least we should be conducting 3 quizzes till 5th of, no, 2 quizzes till 5th of November. So today is 24th of October. So just be prepared, and everything will be on LMS, and I'll inform if there's anything else to let you know. Okay, fine.
Yes, ma'am.
Yes, ma'am.
Okay, Vicha. Thank you, and we'll start this in the next lecture.
Fine.